Hello. In this video, we're going to show how to use the Buckley Leverett solution to construct recovery curves. So plots of how much you have recovered, the pore volumes recovered, it's going to turn out to be, against the pore volumes produced. And we're going to use the Buckley Leverett solution that was introduced in the previous video. So what I want to do now is to go to the whiteboard. And what you see here is that I've already prepared a diagram, a fractional flow diagram, and hopefully this will clarify some of the points with the previous solution and then allow us to continue. So let me show you what we're indicating here. Okay, this is the fractional flow of water, FW. This labels FW equals 1. This point is 0. Okay. On this axis, this is the water saturation. This is the initial water saturation here. This point, which is the end point, and indicate here, is 1 minus SOR. Okay, 1 minus the residual saturation. So what is shown in black is the fractional flow curve itself. What is shown here in green is the shock construction, where this point here is tangent to the curve. So the shock is a line from SWI to the tangent to the curve. So it just hits it here, where the slope of the line is equal to the slope of the fractional flow. Okay? So that then indicates the saturation. This saturation here is the saturation at the shock, which we said was SW left. It's the saturation to the left of the shock. To the right of the shock, it's SWI. Okay. So we constructed our Buckley Leverett solution in the previous video. But now what I want to do is I want to calculate recovery. Okay? And I'm going to define recovery in this way. NPD is the pore volumes of oil produced. Okay. Now what I want to do is just run through that sort of physically, and then with a plot, which I'm going to do here. Okay. And let us think about what that means. So what we're going to show here on this graph is going to be NPD as a function of how much water we've injected, which is TD, which is the dimensionless time, which is the number of pore volumes of water injected. So let's have a look at this. What's the maximum amount that we can produce? Okay, well, the maximum amount we can produce, if we look at this, is we start with an initial water saturation SWI, and at the end of the displacement, we'll get to a maximum water saturation 1 minus SOR. So the change in saturation, which is our recovery, because the water is the oil is replaced by water, is 1 minus SOR minus SWI. Now at this point you might think, oh yeah, but it's pore volumes. That sounds confusing. No, the pore volumes recovered. Well, imagine you go from a water saturation of 0 to a water saturation of 1. You've recovered the entire pore volume, haven't you? So that's 1. So if the saturation goes up by 1, NPD goes up by 1. So it's proportional to saturation, actually. It's defined to be easy, not defined to sort of have to get your brain around porosity and think of putting it in an equation. No, it should be, I mean, I won't say obvious, but that's what it is, right? It's defined that way to make it easy. Okay, now we imagine we got the Buckley Leverett solution, and I'm going to show it schematically here, and then I might get rid of it because this was presented in the previous video. You had a constant state in general, a rarefaction, a shock, and something like this. Okay. So this is your initial water saturation. This is 1 minus SOR minus SWI. right? Everything is small, this is your shock. Now, imagine that your production well at a given time is here. So your production well is at XD equals 1. And VD is XD over TD. So imagine that I've chosen a specific time. And so this now is my XD on this axis. It has exactly the same shape. Okay? And so this is my distance. This is my distance 0 at the injection well. This is my production. If I'm before breakthrough, that is before the shock reaches the well, okay, because over time this is going to be moving, then the only thing that's flowing is oil. Although there's water present, that water is immobile. So if I inject a cubic meter of water, and this is at reservoir conditions, so I can inject a cubic meter of water, what do I produce? Cubic meter of oil. So MPD, the amount of oil I produce, is proportional to TD. And they're both measured in terms of pore volume. So again, there's no sort of conversion factor you need to worry about. So to begin with, okay, when we're in this region, which if you remember before I wrote as I showed in red because it was a constant state, then to begin with, this plot is MPD equals TD. Then we know that we have this maximum here. So when do we reach the maximum saturation? When have we essentially swept water throughout the entire domain, leaving just residual oil behind? Well, we know this because if we look here, this is the other constant state, if you recall, okay? And it will be moving, right? This maximum saturation will be moving at a speed VD min. And VD min is the slope of the fractional flow at 1 minus SOR. That was in the previous video. Now, VD min can be 0, right? Or it can be a finite value. But at what time does that happen? Well, if XD equals 1 at the production well, and I'm moving at a speed VD, then the time T is simply XD over VD, right? And XD is 1. So the time for any wave moving with a speed VD to reach the production well is 1 over its velocity. So in this case, we get to maximum recovery, right? Say here at 1 over VD min. So this point would represent when we reach this. Often VD min is 0. What happens if it's 0? Well, then the time is infinite. So in fact, this is an asymptote. You reach this asymptotically, okay? You never actually quite get there. But now, what about in between? What does this production curve look like in this region here? Okay, so I've just drawn something that's plausible, but it's not necessarily exactly correct. How did I get that? So what we're looking at now is a situation as follows. We're looking at later time. Okay, so if we redraw this, okay, so at a later time, right? We're looking like this, and then the Buckley Leverett profile, the same shape as I had before, has gone beyond the production well. Now, don't worry about what's happened here. All of that oil has been produced, right? There's nothing beyond XD equals 1 because it's come out of the well, right? Which is what our interest is, okay? But what we're interested in is this region here, which is from XD equals 1 to XD equals 0. Okay? So it's this region that is our interest. The way in which we can think about this is as follows, is imagine I could define an average saturation here. Right? So I'm going to call it SW bar, and the saturation here is SW1 because it's the saturation at XD equals 1. So if that's the average saturation, then what we've done is we've gone from SWI to this average value SW bar. So the pore volumes of oil produced is going to be SW bar minus SWI. Okay. Does that make sense? Yeah. Okay. Now, let's just go through this. We know the shock speed as well, okay, and that was indicated in green. The shock speed is VDS. So if MPD equals TD and TD is 1 over VD, then the shock arrives, okay, the point at which the shock arrives is at a TD 1 over VDS. Right? 1 over the shock speed, and this is also 1 over VDS. And VDS here, this is my FW left, my shock speed is FW left minus right, which is 0, over SW left minus SW right, which is also SWI. So 1 over that is the change in saturation divided by the fractional flow at the shock. Okay, so we have this unit slope recovery. There is a finite time at which this shock reaches the well, and we know the speed, so we know the time. So we know this point, which is where the shock arrives. We know either it never quite gets the maximum saturation or it does at a finite time, indicated here. Okay, so that's that point. But now we want to know the recovery in between, and that's given by this average saturation. Okay, so how do we find this average saturation? So the way in which we do this is the average saturation, SW bar, is an integral between 0 and 1 of SW dxd, right? Because it's the integral of the saturation over xd divided by the distance, which is 1. Okay, so that's your average saturation. Now, that integral is one of these things. It looks simple, but how do we do it? And it turns out we can do it by integrating by parts. And you see, we can't do it by parts because there are no parts. But I've put in a 1 there. So 1 is one of the parts and SW is the other. So if you remember your integration by parts, it's where you integrate this one, which is XD, and you've got SW. And then you integrate the 1 again, right? So that's XD. And then you differentiate the other, the SW by the XD. XD. Okay. So let's have a look at that. All right, things now begin to simplify. So if we look at this, right, we can rewrite that as XD dsW. And at XD equals 0, SW is 1 minus SOR. And at XD equals 1, actually the saturation is SW1, by definition. Okay. This term, right, is the integral. It's obviously 1 times SW1, okay, minus 0. So this becomes SW1. So we've got SW1 minus this bit here. Okay. Now at this point, I need a little bit more, I won't say room on my graph, so on the whiteboard. So I don't want to eliminate the fractional flow curve. Actually, what I'm going to have to do is, I think I said already, I'm going to actually get rid of this solution because we're not using it. The only thing you need now is to know that we're in the rarefaction and the saturation at XD equals 1 at the production well is SW1. Okay? So if we're in the rarefaction, we know what the velocity is. Sorry, we're using the wrong color. We should be using blue for this. VD is dFW by dSW, which is XD over TD. Okay, so if we look here, we've got an XD dSW. So XD dSW is equal to TD, whatever the dimensionless time is, okay? Right, and we actually know what the dimensionless time is. I'm going to show that in a bit, dFW. You might say, well, what is the dimensionless time? Well, we know what the dimensionless time is. TD is 1 over VD, right, which is 1 over dFW by dSW, and that's evaluated at SW1, right? So the time we've got this rarefaction, it's got to the production well, it's on the rarefaction, it has a speed dFds, so the time is 1 over dFds at the specific value of saturation that we have in that, right? So it's 1 over dFW at SW1. Okay, so it is, and it's a number, it's not some variable that we have to integrate, there is a given time, click on my stopwatch, now what am I seeing? Okay, so it's a constant, it's just something I have to calculate. Okay, so this integral, this x ds becomes just a df. Td comes out, okay, and it's just a df. So this integral then, and I will go back to black so that we can see that we're actually looking at this integral. SW bar is SW1, okay? Then we got minus Td, the integral of df. So it's just f, isn't it? It's FW. And then it's evaluated at SW1, it's FW1, right? Whatever it is at some point. And then at 1 minus SOR, it's 1. So this can be rewritten as it. Okay, so that actually turns out to be the expression, the average saturation, and then from which we can find the recovery, is some SW plus TD, which is 1 over the gradient, 1 minus FW1. And what that represents, it's correct, it allows you to calculate, right, at any point on this curve, to calculate recovery, but sometimes that seems a bit abstract. So let's go through it, and for those of you with eagle eyes, you might have been wondering what was that blue line that was there on the graph. So let me explain. So what you do, and you can do this graphically, is you take a point on the rarefaction beyond the shock. Okay, you pick a point, right? Remember, as an engineer, you are making decisions, you are doing things. You don't just sit there and expect a point to appear, okay? So you're going to do the calculation. And that point is going to be at your value of saturation, which is SW1. Okay, so this is SW1. Down here, SW1. Okay. The gradient, dFds, is the speed. The TD we're looking at is 1 over the gradient. So on this graph, if you've calculated the gradient, you've actually put a slope here and calculated, dy by dx, okay? Then 1 over that gradient is your TD. Okay, so this you can call TD1, if you like. Okay. That will be some value here. Now, how do I calculate MPD? Well, it turns out this expression, if we look at it, is SW1 plus 1 minus FW1 over the gradient. But 1 minus FW1, if we extend this line to F equals 1 here, this value of F is FW1. So if you look at this 1 minus FW1 is the change in Y. We want the change in X. Well, we know that slope, right, is dFds, okay? And slope is 1 over TD, right? Because the slope is TD. So the delta S, right, is TD delta F. So TD delta F, which is this bit, is the change in saturation. And so this average saturation, right, which is now, it's getting a bit busy, this graph, so maybe we could erase some of the things we not actually using anymore here, okay? All right, because that's that integral, so let's get rid of that. So the way in which you can do it graphically, if you're inclined, is as follows: is if you take, this is SW1, so this is this value here, you then take the tangent to this slope, extrapolate it to F equals 1, and the saturation there, and I agree that there's not the best vertical lines in the world, this is your SW bar. Okay, that's your average saturation. Okay? And your recovery is your average saturation minus SWI. So it enables you to then find the value here, which is right as SW bar minus SW. Now, if you don't quite get that, it's not that interesting. It's not super complex or obscure mathematics, right? My recommendation is to sort of go through that yourself. But this expression is equivalent to essentially taking a tangent and reading it off. And so traditionally, what people used to do when the Buckley Leverett equation was first presented in the 1940s would be that you would plot a graph by hand, and with a ruler, you would do this construction. Okay, so it's something you can actually do yourself. Okay, and normally to get a reasonable approximation of this curve, you'd maybe do it at a couple of points, maybe a point here and a point here. As you can see, you know, it gets quite busy, and that's true if you do it graphically. And then that gives you a recovery calculation. You know, it's not beyond the sophistication of most people looking at this to be able to do it. Well, I could do this, you know, in a spreadsheet, right, on that lab. You know, is it an afternoon's work? Not this terribly busy afternoon, is it, to calculate this? So it is something that in principle you can calculate as accurately as you like, as long as you've got a fractional flow curve. But traditionally it is done in this graphical fashion. So what you have here now is a way of calculating, right? You start with a fractional flow. You can calculate the saturation profile, that was the previous video, and then you can calculate a recovery plot, and that gives you the amount that you recover. So I think that's said enough on that topic here. I'm going to get out of it now. Okay, so that's basically completed the quite Buckley Leverett solution. Okay, we've got the equations. We've calculated saturation as a function of dimensionless velocity, which you can convert to distance quite easily, hopefully, and you can get a recovery. What we're going to talk about in the subsequent video is how you actually use this and how you can use this quite usefully to analyze real data, which is obviously relaxes some of the assumptions. You know, we don't have a one-dimensional flow to start. But I'll finish this sequence here. Thank you very much.